Hi. So I'd like you to be able to do the calculus problems at home, at least number one, number two, and number 3A. So I'm not quite sure how far I'm going to get in the class, but I thought I would go over some of the stuff that I would have done at the very end of class, or just give you another example so that you know how to do these problems. So I'm going to share my screen with you, and then we're going to switch over to OneNote, and I'll use my tablet to explain what I need to explain. So I wanted to say that for a single variable function, like, f of x, whatever it might look like, if a function looks like that. And if you take the point here, let's take a point x1, and you think about the derivative at that point, that's the slope at x1, right? And that is the derivative df dx at x1, okay? Now, if you have a function that is a multivariable function, so you can have f of xy, for example. So now you have two, or even you can have more variables than that. But for this example, I'm just going to show you two because it's the only easy one to show. Then you could think about what you have here, right? As you have, you could call it z if you want, is f of xy. You could think about it as being a surface above the xy plane. Okay, that is that every xy, here is AB, for example, and here is the point above the surface, above the x. Doesn't have to be above; it could be below the xy plane, but it is a value that corresponds to every point in this entire xy plane here, and it either goes above the plane or below the plane. And if you connect all these points together, you would have a surface. So I guess I would say that this f of xy can be thought of as a surface. And the easiest thing would be to picture it as being a surface above the plane. Everything's positive. It's easy to picture, like the drawing I drew in class. But of course, it could be much more complicated looking than that. So when you have a function of more than one variable, so here's the x-axis, and here's the y-axis, and here's the sort of f of xy, right, which we often would call the z-axis, then what you can do is you can cut this surface parallel to the x-axis. So that would be making a cut like this. Okay, sort of cut it like this. Or you could cut that surface parallel to the y-axis, which is what this cut is doing here. Right, so this is cutting the surface parallel to the y-axis. And then you could see that you can have a slope. You will have a slope. You will have this blue slope here, right? This arrow is pointing to the blue slope, and that is the slope in the y direction. And then over here, you have this slope in the x direction. Okay, and we call the slope in the y direction, instead of calling it a derivative, we call it a partial derivative. So this little symbol here is a partial derivative. We still say d. We still say it's df dy, or partial f partial y. So you would say df dy, or partial f partial y, to remind you that there is another derivative as well, and that is the slope in the perpendicular direction, the slope in the x direction, which we would call df dx, or partial f partial x. Okay. All right. So how do you handle these? How do you find these derivatives? All right. So I think I did one example in class, but if I didn't get to it, I'll show you one now. All right. So suppose we have an even more complicated example. suppose we have a 3-variable function. Now, this would be it would be impossible to draw in, you know, in our world because we don't have enough dimensions. We can easily show what it looks like when you have a function of 2 variables. So every point in this plane has a point up or down that is the function's value. But what about if you start out with 3 variables, say x, y, and z, right? So you have f of x, y, and z. Okay, so you couldn't illustrate that as a surface because you don't have 3 dimensions from which you could go up or down, giving a 4th, right? But you could have a function, and there's lots of functions like this. Okay, you could have, here's a function, 16 z y squared sine x. I mean, it's a weird function. I don't want to have to draw it or anything. Well, you can't draw it anyway in 3 dimensions. But you can find its partial derivatives with respect to x, with respect to y, and the partial derivative with respect to z. Okay, so let's find partial f, partial x. So what we do, first of all, we take a look at this function and we write it. What I would do is I'd put the constants in front of it. So I'm not getting the partial derivative yet. That's going to be further down. So I would write it with all the things that I'm going to hold constant in front of it. Now, if I'm differentiating with respect to x, I'm going to hold y and z constant. Okay, so that means everything with a y or a z, I'm going to put it in front. It's already in front. So these I'm going to treat as constants. Okay, so we know that the derivative of a constant times a function is equal to the constant times the derivative of the function. I hate using x for times. Let's just write times. Okay, so that would mean that df, dx would be those constants times the derivative. Now it's just a derivative because there's only one variable with respect to x of sine x. Well, what's that? Well, the derivative of sine is cosine. Here's your constants, and now I just write cosine x. So this is the partial derivative of that function with respect to x. And I just want to add that in physical chemistry, when we have partial derivatives, sometimes we write it this way. And what this means is that you have differentiated f with respect to x, keeping y and z constant. Now in math, they don't bother with this, but sometimes in physical chemistry books, you'll see that. All right, so let's find the other derivatives then. We still have f of x, y, z equals 16 z y squared sine x. And now, how would I take, partial derivative of f with respect now to y? Okay, so once again, I'm going to write this. I'm going to keep x and z constant because I'm differentiating with respect to y. So I'm going to keep x and z constant. So I'm going to put all the x's and z's in front. So these are constants, or I can treat them that way. And then I just have the y squared to differentiate. So df dy is then 16 z sine x times the derivative of y squared with respect to y. Okay, what's that? That's 2y. So this becomes 16 z sine x times 2y, or 16 times 2 is 32, 32 y z sine x. See if that agrees with my notes. Yes, it does. Okay, so we have one more derivative to do. So I hope that you can do this, df dz. You should be able to figure out that this comes out to 16 y squared sine x, okay? So I'd like you to show that as your practice. And once you're done with that, you should be able to do these calculus problems, okay? So here I have a function of x and y, and I'd like you to find the partial derivatives with respect to x and y. Then I have another example. So this is a sheet that's posted on Blackboard. You should be able to get it. Now here we start to look at, you could recognize this equation. You know, we're going to be using the ideal gas law. If you have 1 mole, then PV is RT. Oh, I guess I didn't have n equals 1 there. That's okay. Let's just do this. So you could see that P is nRT over V. So you could think of P as being a function of volume and temperature. And actually, sort of implied in all this is that n is constant. All right, so what this part is asking you is to find the derivative of P with respect to T, the partial derivative, and the partial derivative of P with respect to V. Okay, and we'll go over this in class on Wednesday.